postgraduate and PhD program is also running?
Not PhD, but post graduation is there for many of the BTech programs,
Many
and
of
as well
the
as MBA is also there.
Oh, great. Oh, great. Oh, great. So must be the student strength must be very high in the institution.
Yeah. Number is good.
Oh, great.
And that too, it's been I think 25 years since the institute established.
Oh, it's a quite old institute. Yes, I saw that.
Mm.
Great. Vijayawada means I have been passed through the station while going to Chennai or somewhere, I believe.
Yeah, that's true. It's a much popular station.
Yes. When
And the east.
I came out of the station, I did not saw the city. I think I have to come down sometime.
Yeah, definitely you are welcome, man. If time permits, I will definitely allow you for the physical session as well.
Right. I think we should go back to our old days before COVID, whenever we are organizing this kind of a seminar or something, we have to call the expert in person.
Yeah, that's a great feeling. Yeah. Okay, so we are mostly running on time. Dr. Yuvaraj, maybe it's already 7 o'clock. Let's start with your discussion. After that, I will hand over the session to you. Okay?
Sure. Please start.
Yeah, good evening, Dr. Yuvaraj and all my dear participants. We welcome you all to another informative session on day 5 on this wonderful 2 weeks AICT sponsored Atal FDP on applications of IoT in mechanical engineering. Today, we are glad to have an eminent speaker, Dr. Yuvraj Kumar Madhukar, to share his knowledge on the topic in situ monitoring and feedback control in the GTAW and or VAM processes for Industry 4.0 application. Dr. Yuvraj Madhukar is currently working as an assistant professor in the Department of Mechanical Engineering, IIT Indore. He pursued his master's in Design and Production Engineering from NIT Durgapur in the year 2010. He received his PhD from IIT Kharagpur in 2016. He was research associate during 2015 to 17 at Heriot-Watt University, Edinburgh, UK. His area of research includes water-assisted laser material processing, wire arc additive manufacturing, its monitoring and control. He has co-authored several journals, conference papers, and book chapters. He has been awarded a core research grant in 2021 from SERB and Advanced Manufacturing Technology 22 DST grant for conducting research in the field of wire laser based additive manufacturing, and recently filed a patent in the same field. With this brief introduction, I am handing over the session to Dr. Yuvraj.
Thank you, Dr. Ramakrishna, for such a brief introduction and inviting me for this lecture series. Actually, those who doesn't know, actually our history for me and Ramakrishna is basically we've been in the same hostel when we were studying for the PhD. His room was opposite to mine. So we have a very close connection. We know each other. It was a wonderful journey to come back again and chat with each other. So thank you so much, and I think we can start with our presentation. So the title for this today's presentation is, as Dr. Ramakrishna mentioned, it is monitoring and feedback control in the GTAW construction of welding and wire tie to manufacturing process for Industry 4.0 application. Now, if you talk about the additive manufacturing, since we are going to cover the wire additive manufacturing, if you talk about the additive manufacturing, I think these steps might have been already covered in this lecture series. This basically consists of 5 steps. The additive manufacturing process consists of 5 steps. First, of course, the computer-aided design. Now, in order to make the design, we can go either for the forward engineering or the reverse engineering method. Both the method is fine. However, at the end of the day, we have to end up with a CAD model of a file, because for additive manufacturing application, it is the CAD model is required. It is the desktop integrated manufacturing process. That's why for the long period of time, the additive manufacturing process has also been called as a desktop manufacturing. So here, the involvement or the manufacturing of a product is required through a CAD model. So we do require a CAD model in case of additive manufacturing process. The preparation of this CAD model can be taken by either with the forward engineering method on which we have a concept, then after we can engineering the product in order to get the product, or in some cases we may need to go for the reverse engineering in order to prepare the CAD model or the concept or the idea. Then again the next step comes into the convert this CAD model into the universally used STL file format. This is a specific file format in which typically the additive manufacturing process runs. However, there are some other file formats as well in which we can convert our CAD model file for making of an additive manufacturing product. However, among many others, .stl file format is the most famous one because of its simplicity. The third step of this additive manufacturing process goes to the slicing, because in case of additive manufacturing, it is nothing but a layer by layer manufacturing process. So we have to divide this CAD model into the number of planes. So this dividing the number of a plane business basically we do into the slicing step. Here, each slice thickness is representing each slice layer is representing the thickness of the individual layer. Now depends on a process we've been working for, this thickness may vary, depends on the material we are dealing with, whether it is a mild steel, stainless steel, metals, non-metal, polymer, polymer, metals, and wire form, powder form. Depends on a situation, we may need to optimize this thickness. Then of course the fourth step of additive manufacturing comes making of this product. We can go for the different additive manufacturing process. Again, we have to choose the appropriate additive manufacturing method, depends on which material we are dealing with, whether it is a metal, whether it is a polymer, whether it is in a powder form, whether it is in a wire form, whether it is in a liquid form. So all these things we have to consider in order to choose the appropriate additive manufacturing method. It could be the powder bed fusion method, it could be the laser rapid manufacturing process, laser engineered net shaping process, directed energy deposition process, so by the additive manufacturing process, laser additive manufacturing process, and others. Now the fifth step of this additive manufacturing process involves yes, in case of additive manufacturing process, the quality of a part we get is certainly required the post-processing in terms of both increasing the properties, mechanical properties of the part, specifically for the metals, as well as its dimensional accuracy has to be improved. In case of additive manufacturing process, we cannot get the finishing of the product as what we are getting in case of a machining process. So if we want that level of a finishing, yes, we have to go for the post-processing. There is no alternative. Now, stereolithography file format or the STL file format is nothing but representing any CAD model into the tessellation, triangular tessellation. While converting it, we have to make sure we are representing the actual CAD model and the number of triangles or the tessellation what we are using, it should not be very much high or it should not be very much low. Otherwise, if it is too much high, we are unnecessarily increasing the computational timings and the computational complexity. If we are making that too much low, it may not be able to approximate the exact size of the part or the product we want to make. For example, when we wanted to make this kind of a nozzle, we gone for the coarse structure as well as the fine structure. When we manufactured the product using both the STL files, we've been observed for the process FDM, fused deposition modeling process. In terms of accuracy, we found there is no difference at all. So while converting the file or the CAD model into the STL file format, we have to ensure we are choosing the number of a tessellation or the triangles as appropriate as possible, which can approximate a better representation of a part can be manufactured, as well as we have to also see which process we are dealing with. So that part we have to take into the consideration. Now, the supports also the essential part of the additive manufacturing process. Whenever we get any overhang features needs to be deposited, since it is a layer by layer manufacturing process, certain supports has to be provided, and there are different mechanisms of it that we have to design using the making of a CAD model itself that we have to provide. Now, when we are going for the slicing, the one thing we need to take into the consideration, slicing is nothing but dividing the CAD model into the number of layers. or defining our thickness. So higher the thickness, lesser the build time. However, it is going to leads to the cups, formation of a cups at the edges. We wanted to make a very much oval shape like this, but we are ended up with the cups over here. So it is not representing the actual shape of the part. If we reduce the layer thickness, yes, we are increasing the dimensional accuracy of the product. However, it is going to take the longer time to deposit because the number of layers has been increased. We reduce the layer thickness. So the number of layers we have to deposit is going to increase. So it is going to take the longer time. So somewhere in between approximation we have to find where the layer thickness shall be best representing the part accuracy. At the same time, the curve size, the error should be as minimum as possible. Apart from that, while doing the slicing, we should choose the part orientation where this, as much as possible, these errors can be avoided. For example, here we could see if we want to make a Zomos kind of a shape over here, instead of depositing it in this direction, we can turn it into the 45 degree and we can deposit simple rectangle or the square kind of a box layer by layer. So we can able to reduce the errors what we are getting in this orientation. Similarly, in this case, we could see there is an ellipse kind of a shape. If we make it horizontally, irrespective of the number of layers we are making, certainly there is going to be the certain amount of errors at the part accuracy. On the other hand, yes, if we make it deposit it vertically with the same layer thickness, yes, the number of layers we have to increase. However, it is better approximating the part geometry. So somewhere, whenever we are the bottom line is here, whenever we are going for the slicing, we have to find the appropriate orientation of the part so that it can be better approximation of the geometry. At the same time, we have to ensure the layer thickness what we are choosing, it is a better approximation of the part or the product so that the post-processing, specifically the machining, can be minimized. Now about the part building, there are different methods for making the part. It could be the liquid-based system like an stereolithography process. It is specifically for the polymer-based additive manufacturing process. For the metal additive manufacturing process, we have got the powder bed fusion process like in selective laser sintering, selective laser melting, and in case there are some other processes on which papers or thin sheet metals can be processed like in laminate object manufacturing, and there are many other additive manufacturing methods. I think at this point of time, all of these additive manufacturing methods must have been covered in a much detail. So I'm skipping this part. Now moving to the today's topic, while our additive manufacturing will discuss in a complete detail its monitoring and control for Industry 4.0 application. So when we talk about the worm, it is a wire arc based additive manufacturing process. Now, in order to uh, go for the application like industry 4.0, smart manufacturing application, all these manufacturing processes are basically involving a computer integration such a way as well as some sensors, some actuators, so that the process or the stage on which the manufacturing process is already in or doing, or the state by which it has been already reached is been known to the operator or the person who is monitoring. So for that, in order to ensure all this part, we need to know the construction of an entire this wire additive manufacturing process. For example, the first one is the power source. What are the kind of a power source we can use for the additive manufacturing process? Now that power source has to be a computer integrated, then only the monitoring and control can be possible. So while choosing the power source, we have to ensure it can be able to either it is coming up with that kind of a facility by manufacturer itself, or we have to make our own electronic system so that we could able to communicate with the power source. So we can use any conventional welding system for the warm application. There is no difficulty in that. However, when we talk about the additive manufacturing application or the computer integrated manufacturing system, or possibly all the welding process or the arc welding power source cannot be used. We have to use some certain power source only, which can be made compatible with the computer, or somehow we could able to communicate with the machine. So that information we have to ensure while buying the power source. However, conventional welding machine can be used for the warm application, no problem at all. Now, since we're talking about the additive manufacturing, since it is a desktop integrated manufacturing process, yes, of course, we require the CNC workstation. Now, if we go to the market in order to buy the CNC workstation, and then the cost is of course going to be the very high. We'll try to see if can be designed the CNC workstation in-house and make it applicable for the additive manufacturing process. Yes, we can design it. It is not very difficult, and designing ourselves also gives us an advantage. What are the parameters what we can control during the deposition or during the manufacturing of the process? You know your product in a better way compared with buying the ready-made CNC workstation and spending a lot of time on learning how to operate it. The third one is the feed material. The feed material in case of a van could be in the form of a wire, it could be in the form of a powder, depending on the process. The fourth one, in case of a wire additive manufacturing, typically it is the mass deposition process. Then the part involved remains a matter of a concern, and the support structure means making or depositing the overhang features is again the matter of concern, and controlling that is again becoming very much difficult. So we'll see there are some recent innovative approaches which has been published, what we have been tried by ourselves here in IIT. You will see those approaches. We'll also see online monitoring of monitoring and in-situ monitoring and control of this entire process, and of course the post-processing. What are the post-processing we can go for so that machining cost we can minimize significantly in case of a worm. Now, if you talk about the power source in case of additive manufacturing process, via additive manufacturing process, the three types of arc process: gas metal arc welding based power source, gas junction arc welding based power source, as well as the plasma arc welding based power source. All three can be used. However, in case of a gas metal arc welding, since here the basic concept of this welding process itself says the wire itself is in an electrode which will generate the arc between the electrode and the workpiece, which will melt and deposit it onto the surface. So in this case, it is the most easiest power source or the welding process we can go for the warm application. However, it has got the certain limitations as well as other cons as well. We'll see that in a detail in the coming slides. In case of a GTAW and the plasma arc welding, here we have got the non-consumable electrode. The stabilized arc is been formed between the tungsten electrode and the workpiece. Yes, of course, both has to be electrically conductive. In case of a worm, the wire as well as the base metal has to be electrically conductive in order to close the circuit. So here we make a stabilized arc between the tungsten electrode and the workpiece, and the wire has to be fed separately for its melting and deposition. That means in case of a GTAW based warm process, we need additional equipment called wire feeder. So that wire feeder we need to buy separately if you want to go for the GTAW based warm process, or in short we can call it as a TIG worm. We can call it as a TIG worm throughout our lecture. So if you want to go for the TIG based worm, then we have to get the additional wire feeder which will feed the wire in the path of a stabilized arc generated between the tungsten electrode and the workpiece. Now here we are introducing the another equipment. Now, whenever we are introducing any other equipment, we have to ensure it should be computer integrated. We should able to communicate to the machine through certain commands, through some certain PLC-based system. So that part we have to ensure whenever we are buying any additional equipment. And then the third power source comes into the picture is basically the plasma arc welding based power source. It is similar to the TIG welding based power source. However, in this case, the energy density what we are getting is relatively higher. Because of that, the quality of a deposition what we are getting is going to be relatively better than the warm TIG process. However, since in this case also it is a non-consumable electrode process, we have to feed the wire separately. In case of a plasma arc welding based warm process, in short, we can call it as a PAW
Sir.
van. But again, in this case, we have to get the another equipment which can wire feeder, which can feed the wire, stabilized as between the tungsten electrode and the workpiece. So any of these three can be used for the warm application. So here are some components which has been the result of a wire cavity manufacturing process. Here we could see the complete propeller, ship propeller has been made using the warm process. Yes, the quality of a deposition or the dimensional accuracy may not be very high as we required for the ship propeller application. So we have to go for the post-processing. Here, one of the components we have to see here how it has been deposited, and after machining how it has been look like. Yes, when we are going for the multi-dimensional components like in a propeller, we may need to go for the more than 3-axis workstation for its deposition. Now, we can also deposit the overhang features, it depends on the situation, as well as if we have a multi-stage workstation. Now, if you're talking about this machining requirement, like here, this is the final product which has been manufactured, and after the machining, this is the final component what we are getting. However, depends on the application of the product, we can selectively machine it and reduce the overall manufacturing cost. For example, here is the image of an alloy wheel you can see over here. In case of an alloy wheel, machining outside is certainly required because we have to fit the tire and it should be the liquid, it should be the air liquid. However, the inner surface, it doesn't require the machining, it doesn't require very high dimension accuracy over there. So we can avoid the machining inside of it, and we can enhance our process efficiency and minimize the post-processing. So whenever we are going for the post-processing, specifically the machining, sometimes we have to be very, very selective, depends on our application. Depends on our application, we should choose which part or which side of the component has to be machined or should be machined so that the unnecessary machining can be avoided. Moving further, let us build our own work system. Can we make our own work system? Moving to the second part, CNC workstation. Can we make our own CNC workstation? So making of a CNC workstation is not a very complex job. We can make it. It's a very simple. Here, basically what we do, we have got the lead screw. Lead screw is nothing but a screw which has got the threads, spiral thread on it, and there's a two shaft. There's a simple straight shaft. There's no thread, nothing on it for the support of it. It is mounted on a one plate with the help of a linear bearing. Now, linear bearing is basically bearing. When we say bearing is nothing but a one shaft is stationary, another shaft, one shaft is stationary, another shaft rotating. The linear bearing is the same thing, however, it moves in a linear direction. So it is nothing but a structure, something like this, on which the number of metal balls is there, which can move give the reciprocating motion. So here what you could see is with what we can see over here is the linear bearing. It is supported on the same shaft. Now this lead screw is been at the center over here. We have got the ball nut. The purpose of ball nut is similar to the any nut what we could see. It basically can move if we have got the thread. The nut basically, if you rotate the nut, it can move one place to another in a linear direction. Or if we able to rotate the shaft, the nut will automatically move in a linear direction. So here we have got the ball nut at the center, and at the one end we can connect it with some sort of a power transmission device. We can go for the stepper motor, the best option we can go for. Now when the stepper motor rotates this shaft, it moves this nut or the ball nut from this ball nut converts this rotational motion of the shaft to the linear motion. Ultimately, they are going to get, depends on the motion of this motor, either in a clockwise direction or anti-clockwise direction, we could get the reciprocating motion of this entire stage. The same thing can be repeated for the y-axis, and the same thing can be repeated for the z-axis. And in order to provide the structural stability, we can make a simple, this T kind of a structure. This kind of a system, we simply call it as a gantry type of a CNC workstation or the computer numerical control workstation. So making of this thing is not very difficult. We just need a lead screw, two support shaft, ball nut and few linear bearings for the support of it so that it won't twist it completely. Apart from that, we need one stepper motors or the servo motor based stepper motors that we can communicate through a computer, that we can control through some PLC based controller system that we can able to communicate it. So apart from that, we doesn't require anything and we could able to do it. The one thing what you can notice over here, the XY motion, the deposition is going to take place over here. In the Z axis is been provided to the this thing. Now here we have got the breadboard for the holding the torch. Now here we can hold either the MIG torch, metal inert gas based torch, we can hold the tick torch, we can hold the plasma welding based torch, we can hold, in fact, any torch we can hold and do the deposition. And the workpiece is here, the mounting or the deposition plate is here. So we have to connect this plate to the power source. Let us suppose the power source is over here. So we have got the two terminal cathode and the anode. So one terminal has to go to the this torch and the another terminal of this power source. Since it's a warm process, we have to close the circuit. So another terminal of the power source have to connect with this base plate. So this base plate has to be electrically conductive. Now, since we are dealing with a very high current in case of a welding application or the additive manufacturing application, it may happen sometimes some loose current may start flowing. Since all these are the metallic body, it may start flowing and the sum of the current may go to the motor itself and it may burn it. Because in case of a welding, we typically deal with a very high current, maybe 100 amp, 150 amp, 200 amp, in this range of a current we are working. By any chance, if there some of the current is been moved or the leaked, it may go to the motor and it can damage the complete motor. So the idea is we should make it insulated. So here some material what we could see over here is a asbestos based material which has been separating the complete deposition process from its structure. So this is the asbestos based material which is an insulator has been placed over here on which this deposition plate has been mounted. So this part we have to take care while designing this CNC workstation. So this is a simple CNC workstation in which we can go for the X-axis motion, Y-axis motion and the Z-axis motion. Apart from that, there is one more thing we have to notice over here. The XY motion or the deposition plate can give us the XY motion as well as the deposition tab has got only the Z-axis motion. So once we are moving from the deposition of one layer to the another, we need to move just to once this Z-axis. Then after, in order to move in a space of a XY coordinate, only this stage is been moving. That means my torch or our torch remains stationary while depositing and workpiece is moving. It gives us a lot of freedom or lot of stability specifically for the process like a teak based additive manufacturing process, teak worm based additive manufacturing process in which the wire has to be fed into the stabilized arc of a teak. Apart from that, it gives us the advantage when we go for the online monitoring and control, because since the workpiece is moving, any system what I keep in this frame is becomes stationary with respect to this stage. So any sensor, any monitoring system what we could install in the system is going to be a stationary with respect to this stage. So it avoids the unnecessarily vibration what the sensors can face and gives the error result. So this kind of a system can minimize or the best suited for the where we want to go for the control business, online monitoring and control business. Now this system can give us only the 3 axis of motion. Yes, of course, if we want to go for the 4 axis of workstation or the 5 axis of workstation, we can simply have a chuck which can be connected to again some motor and the gearbox in order to give us the motion in the A axis or the as well as the B axis. A is nothing but a rotational about the X axis and B is nothing but a rotation about the Y axis. So it depends on where we are placing it. We can make it either the 4 axis workstation also we can make it. So this is the system what we have built ourselves. The cost of our entire system that came close to 1 lakh rupees only. Here we could got the stepper motor. Here is the shaft. Here is the lead screw. 2 lead screw for providing the support, and the space of this workstation, what we have been developed in our laboratory over here. It can use in x-axis for nearly 1 meter, and the y-axis it gives the 0.5 meter, and in the z-axis it can use up to close to 0.4 meter of a workspace. It would able to provide no problem at all. Here we have seen GMAW torch is been hanged on this deposit on this breadboard, and here we could see one terminal of the power source of the MIG power source has been connected to the workstation, and here we have got our stepper motor. Now if we see the control system, since we are dealing with the additive manufacturing process, which is the computer integrated additive process, so we need to communicate to the machine, we need to communicate to all these motors, and it should respond with respect to the command we are going to write. So we need, ultimately we could say, we need a PC interface, personal computer interface. So for that, typically we require the CNC control ports or the PLC is required. Now if we look for the CNC control board, the cost of a CNC control board, it is easily available in the market. The cost of CNC control board goes, it starts from nearly 10,000 to 15,000 rupees. It can go up to few crores rupees. So the choice is ours. We can go for the anyone. It doesn't matter. If you ask it to me, I would always suggest go for the as cheapest one is possible, so that when it get damaged, we can throw it and buy the new one. The another advantage for the going for the cheaper one is basically it gives us the freedom to incorporate a different kind of motors and the actuators, different sensors, triggering, because since we have to incorporate now the building power source, wire feeder, or some sensors for the monitoring, all those things we have to incorporate into the PLC workstation or the PLC circuit board. So that's why we should go for the as cheaper as possible, so that while trying it, since we are beginners, while trying it, even something goes wrong and if the PLC get damaged, we can just throw it and buy the new one. The costlier ones are good. Of course, it gives a very good accuracy. However, it comes with their own complexity. Many of them come with the LCD workstation and all. A lot of fancy stuff. Probably you have to spend a lot of time to learning it. Now, we need a DC power source is typically required for running this stepper motors, which will connect it to all the three X, Y, Z stepper motors. And the stepper motor required a drive that or the motor driver, which we could see over here, which will be connected further to the CNC control board, and which will communicate to the PC further. So the stepper motor is connected to the power source, is connected to the stepper motor, is also connected to the driver. The specific driver is required for each stepper motor or maybe the servo motor, and it is further connected to the CNC control board, and the CNC control board is going to communicate to the PC. It could be the simple Visa interface, can be used for this purpose, no problem at all. Now the workstation what we have developed over here, this is the percentage of error what we been observed depends on a different traveling distance. Now here we could see if we reduce the travel length, the percentage of error is increasing. Now it is because of this stepper motors. Whenever we send the command through certain program from PC to the CNC control board, and which goes to the driver, then after the axis of motor rotates in a rotational motion, and that is going to further convert it into the linear motion with the help of an ball screw. So whenever we give the command to the motor to rotate, to accelerate or move at a speed of a v or rotate at a speed of a v, practically it doesn't achieve that v instantly. It takes certain time to accelerate the velocity. It remains in that velocity for the time duration we are asking it. Then after, again it takes certain time to deaccelerate to zero as soon as we ask it to stop. So this is the total time duration what we are commanding the motor to run. However, it takes certain time to accelerate in order to achieve the desired speed. Then after it stays in that speed, then after it again come down, deaccelerate in order to come down to the zero speed. Now, if the distance is very much small, then it takes longer time. If the distance is small, then since this timing or the maximum acceleration speed of a motor is almost constant, it is the manufacturing constant, then if the shorter distance is there, with respect to the distance, this error becomes more. So practically, we might be getting like this, and it may not be even achieving what the peak velocity we will commanding. So here we could see when we are giving the travel length of nearly 50 mm, the percentage is error is less than a 1%. However, when we are going for the distance of a 0.1 mm, the percentage of error is nearly 20%. So the bottom line is over here, for the shorter distance, the percentage of error is going to be the more. So whenever we are buying these stepper motors, we have to ensure this acceleration and deceleration time for this stepper motor should be as minimum as possible. So that part we have to take into the consideration whenever we are buying the stepper motors. Otherwise, the cost of a stepper motors, again, we can get into the few hundred rupees and it goes up to few lakh rupees. So anyone can probably do the job. However, when we talk about the monitoring and control, any motor is not going to do the job, because at this period of a time when it is taking certain time to accelerate it, practically we are depositing the more amount of material compared to the stage over here. So it will give different result, it will give the different result. So all these things needs to be considered while designing this CNC workstation. Apart from that, I think we are good to go now. Now we can, as been mentioned over here, we can hang either the GMAW based power source for the WAM application. We can go for the GTAW based power source for the WAM application. We can also hang the plasma welding torch for the WAM application. No problem at all. So CNC workstation has been finished, and then after we can hang any power source for its deposition. However, if you want to go for the warm pig or warm plasma, then we have to use another machine called wire feeder for feeding of the wire. So MIG-based additive manufacturing process, it is similar to the fused deposition modeling process, in which we have got the polymer wire and the coil to heat it and deposit it into the surface. However, instead of a polymer, here we use the metal wire has been used. The process involves melting of a metal wire using an electric arc. Therefore, the process is limited to conducting wire and deposition base only. Since in case of a arc-based process, it is the we have to generate the arc between the electrode and the workpiece. It is limited between the conducting material only. The process needs automated system to execute the .stl files. For that only we will make this CNC workstation. Often successive cooling is required due to intense heating and relatively bigger melt pool as compared to the laser-based system. Yes, in case of a WAM process, whether it is the WAM MIG, WAM TIG, WAM plasma, the melt pool size typically we are dealing with here is relatively higher. So successive cooling after the deposition of each layer is often required. So this is the same workstation integrated with the MIG setup. Here we could see. And now, in order to execute the .stl file format or the .stl file for the WOM application, and in order to communicate through a PC to a CNC control system or the PLC based control system, there are a number of open source platforms are there. We have to write a code in that. Typically, most of these PLC based control systems works on a GM coding, and that code we have to write it ourselves, or whenever we are doing the slicing, then while the result of a slicing is nothing but a GM coding, that GM codes we have to feed into this CNC control board in order to make the movement of it. Now at the same time, whenever the stage starts moving, we have to ensure the power source also triggers, or the power source is also communicating to the communicated to the our PC, or it is responding with the PC command. So for that we have to connect this power source with our PLC over here again with the help of some sort of a relay. Here we could see GMAW torch. We can connect it to the some sort of a relay. Relay is nothing but a electrical switch which can be triggered with respect to a certain load, certain voltage, typically 0 to 5 volt DC or 0 to 10 volt DC. So whenever we are getting the GM code after the slicing using any software, while incorporating or loading that software into the PLC system, we have to communicate additional line, or we have to write additional line to in order to trigger the relay. That relay is going to send the command to the GMAW torch to initiate or start the deposition process. So this part we have to do additionally what we are getting from the result of a slicing process. Most of the conventional slicing softwares like a Slice 3 or Cura is been designed explicitly for the fuse deposition modeling process or this particular FDM process. So all the information what has been there in a code probably is not be useful for the WAN. Since we are designing our entire system ourselves, some additional lines we may need to use. One of them includes connecting a relay to our PLC control system and triggering it as soon as the stepper motors starts moving or the G code starts. If you are ensuring that part, movement of a CNC workstation, movement of the CNC workstation and the ignition of a arc is going to take place at the same point of a time. So this is some of the videos what we will recorded during the deposition. The, the motivation behind showing this video is that at the beginning, while we're starting the process, we need to optimize the deposition parameters. There's a very complex process. The wire feeding with the speed by which the stage is moving, needs to be optimized. Here in this particular, the first video we could see, in sometimes the arc is getting off during the process itself. Here we could see the arc is not remains consistent. It is getting off during the process compared to the other process which is becoming almost continuous. Actually, all these things affects the part quality what we are depositing. Here we could see all of this process means at the beginning probably we are going to end up with the structure depositing like this. A lot of undercuts on a deposition. Even after the machining, there are some blowholes. It is not giving the very good dimensional accuracy. At the beginning, yes, we are going to come across this kind of a situation only. However, we have to understand the basics of wire arc based additive manufacturing process. Now, if we talk specifically about the MIG-based additive manufacturing process, so MIG is nothing but a constant voltage process, and the current will be determined based on the resistance between the electrode and the workpiece. So uh, uh, look for the one case when wire feed speed is, let us suppose, 3 meters per minute, and the commanded voltage is, let us suppose, 17 volt. We are getting the deposited bit something like this. The bit is here more, here it is again lesser, here more, again here lesser, again more, again means we are not getting the consistent, very good deposited bit. Now, if then what we did, we recorded the in situ the welding parameter. Welding parameter means welding voltage and the current. So here we could see, since it is a constant voltage process, the MIG is a constant voltage process. Once the arc has been stabilized, the voltage becomes almost stationary, close to the what we've been commanded, but it is gone relatively more, 19.2 volts. However, the current is keep on fluctuating throughout the deposition. It's basically because of probably the amount of energy what we are giving is not sufficient enough, and the vial when the vial is, because this energy is not sufficient enough and the vial feeding rate is relatively higher compared to the amount of energy what we are giving, and because of that probably there is a short circuiting between the vial and the base plate, and in order to break the circuit and keep the arc stable, machine automatically increases the current in order to keep the arc stable. Now if we see we can typically we can distinguish 4 zones where the current has been increased significantly: 1, 2, 3, and the 4. Now, wherever the current has been increased, since it is a constant voltage process, the overall power has been increased. The amount of energy what we are giving is got increased, and because of that, probably here also the more melting we could see in a 4 different zones: 1, 2, 3, and the 4. That means we need to find the appropriate range of a parameter in which it should be stable as far as possible. Voltage is going to be almost stable since it is a constant voltage process. However, the current has to be a stable as far as possible as well. We need to find the optimum parameter for the deposition. For example, the other case, when we send the speed, wire feed rate, we kept it 4 meter per minute and the commanded voltage is 22 volt. Here we are getting such a nice deposition, no spatter, nothing over here. And here also we could see, once the voltage has been stabilized, the current become almost stable as well. And because of that, very nice deposition we could able to see. Now, if we calculate the amount of energy input, in this case, we've been giving nearly 0.33 kilojoule per mm, and the previous case, it was nearly close to 0.21 kilojoule per mm. So certainly in this case, without changing the material property, we are giving the very much less amount of energy. So certainly there is a chances of a high chances of a short circuiting, and because of that the current increases wherever the short circuiting is will happen, and because of that we are getting the non-uniformity in deposition. Probably in all these cases something that kind of a situation has been happening. So we need to the bottom line here is we need to optimize the parameter for the additive manufacturing application. So here we could see uh, for the different voltage starting from the 16 volt to 23 volt and the different wire fitted, the different bead property can be found. Here we could see the bead width increases almost linearly with respect to the voltage. However, the bead height remains almost constant. This bead height remains almost constant. However, the bead width is increases linearly with respect to the voltage. Yes, it is quite obvious because since we are increasing the voltage, that means we are increasing the input energy. So it is quite obvious, but we have to optimize it. Once we could able to optimize the parameters, you could see over here such a beautiful shapes we could able to deposit, no problem at all. Here, even in case of a WAM application, we could able to deposit the wall thickness of the order of close to just 2 mm. Some fulcrum shapes, which is resembling the propeller shapes, we can deposit very easily. Moving to the another type of additive manufacturing process, stick-based additive manufacturing process, stick and plasma-based additive manufacturing process. Here, the first, the arc is stabilized, or the electric arc is stabilized between the electrode and the base strip. Further, the wire is fed in arc through additional wire feeder. The deposited layer, bead profile, bead height depends on both the arc, electrode dia, point angle, standard distance, mode of operation, whether it is the AC, DC, arc current, all these parameters play a certain role. So here we got our tick power source, and here we have got the wire feeder. Now, if we go to the market, there are different kind of wire feeders has been available. Some of them can it has been typically called as a cold wire feeder. There are some hot wire feeder is also available. So we can buy any wire feeder we can buy, no problem at all. However, one thing we have to ensure when buying the wire feeder, it should be triggered or can be communicated to this wire feeder through some additional circuitry or through some relay, so that we can connect this wire feeder again, like we've been connected this power source, like we connected this GMW power source. Similarly, we can have over here wire feeder, and that wire feeder can also be connected to the relay, and the formation of a arc is, as soon as the formation of arc has been established or the arc is been stable, the wire feeder should start feeding the wire. So we have to ensure that particular provision is always there in case of a wire feeder. Now, if you go to the market, there are different type of wire feeder is available. If it is sending the wire in a room temperature, typically we call it as a cold wire feeder. If there is a provision for heating the wire, because sometimes preheating the wire gives a certain advantage on deposition, so we call it as a hot wire feeder. There are some wire feeder which can feed the wire in a pulse mode, means a feeding, then stopping, feeding, then stopping. So it can also feed the pulse mode. So different options are available. Of course, with the different functions or many functions, the cost of the wire feeder increases significantly. However, the one feature we have to ensure it should have whenever if you are going for the TIC-based additive manufacturing process or the VAM TIC process, we have to ensure this wire feeder have one more function apart from the external triggering, is nothing but a retaining feature, push-pull mechanism. What is the push-pull mechanism? Is basically in case of if I zoom this area over here, then in case of a peak-based additive manufacturing process, we generate the stabilized arc into the base plate and we feed the wire in this stabilized arc. Now at the edge, once the deposition is been done, when we're depositing over here, at the edge, we have to make sure the wire is been pulled back from this arc zone before the arc is turning off. Otherwise, this wire is going to get stuck to the deposited bead itself. If that situation is happening, every time we have to manually cut this wire. So whenever we are buying the wire feeder, we have to ensure it has the retaining feature inbuilt. Otherwise, we have to cut the wire manually every time, which is not possible when we are dealing with the complex geometry deposition. So we have to make sure the wire is being pulled first before the arc is been triggering. At the same time, while we are starting the deposition, the arc must stabilize between the electrode and the workpiece first. Then after, the wire should start feeding. So this push-pull mechanism must be enabled in the wire feeder. So here we could see how gentle this process is compared to the MIG. There is no spatter at all, and it's a very gentle process. We have to, it is, since in a normal VGA based camera, it is a lot of glowing, we couldn't able to see how the deposition is going. However, when we recorded it using the thermal camera, here we could see first the arc has been stabilized. Then after, we have to feed the wire into the stabilized arc of a tip. And very nice bead we are getting just behind it. There is no spatter at all. Now, this is the first layer of the deposition, and this is the 11th or 12th layer, I think it is 10th layer of a deposition. Here one thing we have to notice, when we are depositing the first layer, the melt pull side is very much small. Here we could see the melt pull side is very much small compared to the when we are depositing the 10th number of a layer, the melt pull side is significantly larger. This in order to just realize what is the size of this melt pool or the melt puddle, this electrode diameter is 2.5 mm. Considering that, certainly we could say the melt pool size is of the order of nearly 12 to 15 mm. And in these two cases, there was no change in a deposition parameter. That means with increase of number of layers, the melt pool size increases significantly. Now this is something which is going to make our life difficult when we talk about the monitoring and control. So we have to optimize this part as well. Now, if we talk about the arc-based advantages and limitations, yes, of course, we have got the very high rate of deposition, significantly economical, good dimensional accuracy, no control environment, but enough gap is required. Yes, of course, limited to the conducting material. The process needs significant post-processing to improve the dimensional accuracy. Oxidation of the part is one of the major challenge. Often more than 3-axis workstation is required. In case of a TIG-based additive manufacturing, since we have to feed the wires separately, so depends on a direction of a feeding. Like in this case, we are moving in this direction and the wire feeding is going to be from the front. So depends on the direction of a feeding of a wire, whether we are going for the front feeding or the back feeding or the side feeding, it has been observed the bead property, the bead width W and bead height changes. So as well as the amount of input parameters is required is changes. So in case of this additional wire feeding based WAN methods like in WAN peak, WAN plasma, we have to take into the consideration of this part as well. The wire feeding direction does play certain zone. Now this limit, I'll explain it later. Now, in order to increase the this mechanical property of the Bombay additive manufacturing process, if we look into the or dig into the literature, some of the literature we found in order to enhance the mechanical strength of it. One paper we found what they have done basically. Once they are depositing using the tick toys, the wire is fed over here. A mechanical zoner is being used at certain zone when the body is already on elevated temperature at a certain load. This zoler is passing through it, and while it is passing through it, it is defining the grain structure. Here we could see it is as deposited, and the second one is the at 50 kilonewton of a zolar load after each layer of deposition, and the another one is 75 kilonewton of a load after the each layer of deposition. Certainly, we could say in case of a higher load, more dense means grain structure has been formed, which is also reflected in a more hardness of the system. Now, in case of one, the another limitation or the cons we come across is the dimensional accuracy. So for that, hybrid additive manufacturing process has been introduced in which the conventional machining can be performed after deposition of each layer or maybe after deposition of a certain layers. Here we could see once it has been deposited, it has been machining on a top surface as well as the side surface. Now it gives us enhances the dimensional accuracy significantly. However, if you want to implement this kind of a system, certainly we require either the two CNC workstation or a single workstation which are two head CNC workstation. CNC workstation which have got the two heads so that the deposition and machining can be happen simultaneously. However, doing it has got the certain advantage. First of all, certainly it is increasing the dimensional accuracy. However, at the same time, since in case of a arc-based additive manufacturing process, whether it is the MIG, TIG, plasma, uh, the dimensions what we are getting on the surface of the deposition, there's an always certain striation forms, and because of that, the standard distance between the electrode and the workpiece is keep on fluctuating compared to the first layer of a deposition on which we are deposited on a flat bed. So, in case of a WAM process, once the bead is been deposited, certainly the surface has got the certain striation, and that striation plays greater zone for the stabilization of a arc. So if we go for the machining, the situation becomes every layer is been deposited on a flat plate. So for the application like in monitoring control, this kind of a surface gives much more better result and much more control over the uh, much more control on controlling the entire process. As well as it also helps for the machining of intricate shapes, because if the shape is very much complex, sometimes after the complete deposition of a complete product, the tool reachability becomes a matter of concern in case of a WAN. Now, we may need to come across some sort of some innovative ideas for the WAM in order to uh, minimize the requirement of a support structure, because in case of a WAM, the support structure is the biggest enemy, because we could see over here, we saw the melt pool size is relatively very bigger when we go for the 10th deposition further onwards. So the one of the idea what we come across, for example, if you are dealing with the part like this a propeller blade, certainly if you go for the bottom to top deposition, good amount of a support structure would be required, and in case of a WAM, making the support is a huge challenge. So we can modify or come across some sort of innovative ideas in order to minimize this requirement of a support structure. So one such idea could be the going for the radial slicing. So instead of slicing from the bottom to top, we can slice the product radially. Of course, no commercially available slicer or the software can do it. We have to write it our own code using in MATLAB or using in MATLAB. There is no alternative. Or there are some manual methods also there. For example, we can do it in a SolidWorks as well. What we have to do, we have to just radially slice the part of geometry, and with respect to the different coordinate systems xy, xz plane and the xy plane, we have to make a number of lines equal to the layer thickness and try to find the coordinates of each point into the both x, y and the xz plane, and try to find the coordinate of any point in a x, y, z coordinate, collect that data into some Excel file or IGS file format, and further write your own code yourself. Yes, it can do the job, however, it is very laborious. The better way is to write the code in a MATLAB file format, MATLAB platform. We wrote our code over there itself, and let us suppose this is the blade. A different radius of a circle can be used equal to the layer thickness, and it is going to find out the coordinates of each individual point striking on this circle or the layers in both coordinates xz plane and the xy plane, and it can, once we know the coordinates, we can further write the code in the MATLAB itself in order to generate the G code. That G code we can feed into our PLC workstation. So by doing this, we could able to deposit, let us see, in a shaft which is acting as a base, we could able to deposit a propeller blade without the use of a support structure. Now, since we are dealing with the shaft and it is the base plate, it is here we are not depositing on a flat plate and one upon another. We have to go for the workstation which can move the job horizontally about the rotation axis, or the rotation axis is required. So for that, what we can do, we can go for the fourth axis of a workstation. We can build it. Simply here we require the chuck, and the chuck shaft is supported by some sort of a supporters, and the motion we can provide using again the stepper motor, and this again the stepper motor can be connected to our PLC workstation, and we can get the code using our MATLAB programs. So the bottom line over here, what I was trying to say is we may need to come up with the innovative ideas in order to minimize the use of a support structure in case of a van. Otherwise, because the making of a supports is very much difficult in case of a van. However, there's a lot of innovative ideas are coming into the literature. If you look into the literature from nearly 1990s to 2070s, in case of the additive manufacturing, 3D printing, additive manufacturing, the number of applications we see close to, in 2017, it has been gone close to nearly 6,500 number of publications per year. However, in case of a support structure, hardly we are getting 500 number of publication throughout the year. So there's a lot of scope of a research in the field of a making of a support structures. Specifically for the process, making the support structures are very much difficult. So in order to overcome with this problem, so one such idea could be the radial slicing. The another idea for making the support structure, if we see the requirement of a support structure comes only to provide the base for the first layer, and the further layers would be deposited on it. If we talk about the process like a selective laser sintering, laser engineered net shaping, and direct metal laser sintering, the support structures are often required, depends on the part geometry. The typical structures are lattice support, honeycomb support, unit cell, etc. Achieving this kind of a support structure in case of a worm is relatively very much difficult. So either we can go for the multi-stage workstation and some innovative slicing methods like we did over here, or we have to come up with a certain more innovative ideas. So what we have done over here, we took metallic pillars or cuboid, we could say, of certain dimension, and we arranged it into the array of a row and column, and all these pillars has got the certain holes, one in this side, the another one this side, and we mechanically fasten it using the help of a nut and a bolt, and at top surface here we could see we have got the surface, and here we can use it for the deposition. So we can arrange these pillars or the metallic pillars in an array of a row and column in order to get the desired surface area, and these nuts and bolts has been attached together with the this pillars has been attached together with the help of a nut and bolt. Here is the image of this system we could see over here. Here we have got the number of pillars. Now in this one we could start depositing our part. So here we could see a circle has been deposited on it, and since in case of this hollow cylinder, there are many areas which is not representing the part of the geometry, lot of pillars remains intact. So we can deposit the another part on the same one, and while removing these nuts and bolts, we could able to remove the part very easily without any machining significantly. Now, machining of these pillars is of course required in order to take this part out. However, the situation becomes relatively easier compared to when you're machining the entire base plate in order to take out this part. So, as well as see, we are able to deposit the multiple components on the same base plate, and the post machining is also remains minimized significantly. As well as still some amount of pillars in the inside and here, which does not represent the cross section of the part has been deposited, or the remains intact from receiving any deposition material, can be reused again and again. So this could be the one of the approach by which we could minimize the post processing, or the separation of a part can be made very easier. Now here, what if we could able to achieve this kind of a deposition, if the concept works over here, what we can do, we can think of changing this pillar height. Instead of taking these pillars of a constant height, we can change this height of a pillar in a certain pattern. For example, here we change the pillar height in a certain V pattern. Just step size we have to optimize, so that we have to ensure the deposition is taking place over here, and we should able to deposit this kind of a overhang feature for the worm application as well. So here we could see at the beginning there might be some issues with the deposition. However, as soon as the number of, with the optimization of a parameters, the number of layers is been increasing, we could able to achieve the best deposition like this, no problem at all. So certainly we could able to deposit it. That means by changing the pillar heights, we could able to deposit the overhang features without the use of any additional axis of a motion, what we did in case of a making of a propeller. By changing this pillar height, we can deposit the overhang features. Yes, of course, we have to machine it for its separation. But the challenges what we had in case of a base plate, and then after making some sort of a pillar, then after depositing the overhang feature, is now can be removed completely. So by this method, we could able to minimize the make the support structure in case of a web as well. If we reach to this stage, the another innovative ideas we come into the come across is specifically the result of a conventional machining is nothing but a wastage of this metallic chips. So what we did, we collected this metallic chip from our central workshop, and then after what we did, we compressed it using some sort of a die punch mechanism, and ensuring the thickness of the order of nearly 5 to 7 mm, 3 to 5 mm, 7 mm in this end, ensuring the density of the plate or this porous structure of the order of nearly 40 to 50% of the solid metal plate. Now, it is giving what we did, basically we collected the metal chips and we compressed it, and in order to make the plate which has got basically the porous structure. Now since this metallic chips has got a lot of edges on it, while compressing it, it interlocks each other. So it won't going to disassemble so easily. So since it is the metallic chips, we can use it for the additive manufacturing application. So again, making the arc stabilized between this metallic chip base and chip base and depositing it certainly is going to be the very, very challenging. However, it is feasible. We could able to achieve it. Here we could see there is a metallic base chip on which we deposited this rectangular structure. Now the question comes, how the fusion is going to take place in this case. In case of a solid base, there is a metallurgical bonding between the first layer of deposition and the base plate. What is happening over here in this case, in case of a chip based substrate or the swap based substrate? Here, actually, since we have got this swap substrate, if we look inside of it, it is nothing but a porous, it is nothing but a porous structure which has got a lot of holes on it. So once we are depositing the first layer of a deposition, in case of wire arc IoT manufacturing, ultimately at the end of the day, we are melting the wire and depositing it onto the base. Now, in case of a swap substrate, as soon as we are trying to deposit it on a swap substrate, what is happening? That molten metal starts showing, all the direction of this porous structure, and we are getting the structure similar to the roots of a tree. So this shining portion, what we could see over here, is nothing but a molten metal which been flown in all the direction. If I'm looking from the top, this is the molten metal drop which has been found. So it has started moving in all the direction, and it making the structure similar to the roots of a tree, which is giving the enough strength for the further layers to build up. Here we could see, we could able to deposit nearly 30-40 layers, no problem at all. The dimensional accuracy was very, very good. Yes, of course. And in this case, since some amount in the and after the deposition, with the simple hammering, we could able to take out the part very easily, no problem at all. Yes, some amount of our chips or the swap remains going to get fused with the cross section of the part where the deposition is taking place. However, with the minimal machining, we could able to achieve the very finished surface. It has got the further advantage again when we are dealing with the structure like this, in which we have got, see, here we have got the bigger cylinder, some supporting spokes, and the smaller cylinder. Now making this kind of a structure even with the 5-axis workstation is not possible without the use of a support structure. So what we can do in this case, this is our chip substrate or the swap substrate. We can deposit this bigger cylinder first, then after, since we have got the hollow part, again we fill the swap substrate and deposit this spokes and the central cylinder on the top of it. So we can able to make the swap substrate as a support structure as well. So, and here we could see one of the, this is the same structure which has been deposited over here. This concept we also been patented. With the build of additive manufacturing for the support structure requirement. The bottom line over here, again, what I was trying to say, we have to keep on coming with the innovative ideas wherever we are facing the difficulty. The support structure is one of the major challenge in case of a RAM. However, with the help of these innovative ideas like in radial slicing, pillar substrate, chip-based substrate, we can minimize the requirement of support structure, or even if we could not able to minimize it, we should come across some sort of an innovative idea so that we can able to make the deposition complete. Now, coming to the, once we are able to ensure the deposition is taking place, even if there's an overhang requirement, we can make the supports. Now, the time comes to monitor the process and control it during the deposition itself, so that we can use it for an Industry 4.0 application and some other online based monitoring and smart manufacturing application, some other application. So if you are digging into the literature, there's a number of ways is been reported by which they are saying we can use some sort of optical signals of a visible light, infrared and ultraviolet emission of a plasma, because whenever we are generating the arc, there's a certain amount of emission of a visible light, there's a certain amount of emission of infrared light, there's a certain amount of emission there. So we can use it for the monitoring and control. There are some researchers are saying we can use the photodiode to detect the wide variety of weld defects, and it's for its weld defect, specifically bead width, bead height, blowholes, all this kind of defects can be used. Some people are saying we can use even some acoustic signals, because whenever we are depositing the material, There are certain noises which is comes. So can we use the acoustic signals in order to assure the quality of the deposition? Some of the people are saying we can use the laser triangulation based sensors in order to monitor the bead width and the bead height using the deposition as well. There are a number of approaches is been reported into the literature. However, uh, all these uh, sensors, specifically with the optical sensors, this for visible and infrared light, photodiodes, acoustic methods, doesn't give the uh, doesn't give the uniformity or the well consistency in their results. Depends on the process, it is fluctuating a lot. And specifically, if we talk about the industrial environment where there is a significant amount of dust, fumes, a lot of noise coming from here, there, then implementing this type of sensors in case of a actual world environment is going to be a going to give us a lot of errors. So we have to come up with some other solution. Uh, so we'll see that. So in case of a worm, we require the trivial control on both the position parameter associated with the power source and CNC, such as arc voltage, wire feed speed, standard distance, gas storage, deposition speed, XYZ motion control,
Hello.
power triggering, etc. Therefore, we need to have some sort of a feedback system for the implementing, considering the generated temperature as a primary parameter to control the power ratio. Now, all these sensors may work in a laboratory environment. However, whenever we talk about the industrial environment, there's a lot of noises, lot of lights is coming from here and there. So that sensors may not be able to be useful. However, in case of a WAM, ultimately at the end of the day, what we are doing, we are melting the wire and we are allowing it to deposit solidify it on a base or the already deposited bead. So can we take the temperature as an input signal? Can be considered temperature as a primary parameter to control the rest of the parameter, making some sort of a feedback control system. Making some sort of a feedback control system which will regulate all the input parameters, because the number of parameters we are dealing with is significantly high. We are dealing with the our voltage, our current, then standard distance, gas storage, deposition speed, XYZ motion, power tracking. All those things has to happen on the same point of time, and it should assure the quality of our deposition. So, can we take the temperature, the generated temperature as a primary parameter to control the power ratio or the process completely? It shall regulate the input power to maintain the desired temperature at the desired location, which could correlate with the build quality further on. Since we are dealing with the temperature, our ultimate goal is nothing but to melt the wire and deposit it. Temperature seems to be a good parameter that is basically the result of our input parameter. So we can take the temperature as an input parameter and try to regulate the rest of the parameter, making some sort of a feedback control. So when we are talking about the wire feedback control, then, so if you look into the literature, there is basically three types of a control system I can come across: open loop control system, feed forward control system, and the feedback control system. Open loop control system, let us suppose this is the system, we are giving some input parameter, we are getting certain output. There might be some disturbance coming into the system which is giving us some error, we do not have any control in it. Based on certain experience, we may be able to control the input parameter. In order to just just automate it, the feed forward control system comes into the picture. Whatever the error we are getting, based on the observations, we are trying to minimize the error or modifying our input parameter so that the system can run. And again, whatever the output we are getting, we doesn't have any control in that. We are having control only on the input parameter, and based on the experience, we are modifying our
Not listening class and
signals
you are
in
seeing
order
phone.
to optimize or minimize the errors what we are getting. The feedback control is the best system probably, it seems, because we send the input signal to the system or the process to happen, and whatever the error is coming into the output, based on the output or the error whatever we are getting, making the control system to modify our input parameter in order to minimize this disturbance. So it seems the feedback control system is going to be the best solution among all for our application. Now, there is other reason as well. For going for the feedback based control system, or even if you are going for the feedback based control system, then where to position and where to monitor our temperature. So this is, let us suppose this is the plate on which the heat source has been moving. So we could distinguish the different zones like this. Here at the center we have got the melt pool. Then after we are going to have a partially melted zone, and behind this heating source, let us suppose the heating source is nothing but a area source which has got the area in the form of a circle. Then the melt pool is typically forms in this shape, and in the front of a melt pool we'll have got a partially melted zone, and once the heat is moving in this direction, behind this heating zone we have got the fusion zone in which the solidification is taking place. Now, where to place our temperature monitoring system? Now, in order to understand that, we have to see how heat and any fluid flows. For that, we could see the temperature distribution in a plate for low thermal conductivity material as well as the high thermal conductivity material like an aluminum. So low thermal conductivity material like this low carbon steel, here we could see the area on which the heat contour is being formed is going to be very much small, and behind the heating source it is the heat contour is forming for a longer distance. At the front it is going to be a very lesser distance. If you talk about the high thermal conductivity material, then the area distribution of a heat is relatively more in a front. However, it is happening for the larger area. With respect to the speed of the deposition, for low speed and the high speed of a deposition, here we could see in case of a low speed, the area in a lateral direction is relatively higher. In a front also, the good amount of heating is take place. If we increase the speed, the length is increases significantly. However, the front heating is reduces significantly. With respect to the plate thickness, thin plate and the thick plate about 20 times thicker. Here we could see if we have got the thin plate, more amount of a temperature contours is basically forming on the back side, and very less amount of a temperature contour is been forming on the front side. For higher thickness of a material, yes, there is good amount of a temperature contour forming in the front side. However, again, it is the back side we are getting the more amount of a temperature control. Here, with the help of different diagrams, the bottom line or the information what I was trying to share with respect to the material, whether it is low thermal conductivity, high thermal conductivity, with respect to the speed, with respect to the plate thickness, the temperature control always going to be a lesser at the front, and it is going to be a more at the behind. Now, if it is behind, then the sensing the temperature in this zone probably going to give us the more freedom or the wider area where we can make the control system work. If we want to go for the feed forward control system, then probably we have to put our sensor somewhere around here, which will further try to communicate to our input source. So at such a small distance, specifically when we're talking about the worm-based system on which we are generating the arc, and the arc area itself is of the order of nearly 8 to 10 mm, making this kind of arrangement is going to be very much difficult. That's why feed-forward control possibly is not a good solution when we go for the WAM-based online monitoring and control system. Better to go for the feedback-based control system. We can place our sensor, since we have got the temperature is reducing significantly, reduces over the distance, but it reduces over the certain distance. So we have got the large amount of area for its monitoring and control. So feedback control system seems to be a better choice for going for the this particular column. Now, now at this point of time, we know we can go for the measuring of a temperature in order to control our parameters. We know where we should place it. We should go for the feedback-based control system, and we should try to keep it, our sensor, or try to monitor the temperature behind the earth so that we can make the feedback-based control system, since we are getting the larger area for its monitoring and control, and we are going to get the more stable result over there. Now, what devices we should use for the temperature measurement? So when we talk about the temperature measurement, we end up with the three type of devices only. First one is the thermocouple, the another one is the thermal camera, the third one is the pyrometer. In case of a thermocouple, it is nothing but a we know this device. It works on the principle of a cigarette factor. It is the device in which the thermocouple has to be physically in contact with the surface in order to measure the temperature and in order to measure the temperature. Yes, of course, in case of a WAM application on which we have to deposit the number of layers, probably using the thermocouple is not going to give us the good result, because in this case, maximum we can place our thermocouple at the bottom. Then after we could not able to do it. Otherwise, after every layer we have to drill it and place the thermocouple. So ultimately, for the laboratory experiment or the trial experiment, it may be okay. However, when we talk about the ready-to-use component, the components can be used for the industrial platform. Probably it is not going to give us a good solution. So a thermocouple is good, may be used for the laboratory experiment or laboratory level. However, when we talk about the actual part building, possibly the thermocouple is not a good choice. So another option we left with is the thermal camera. Now the thermal camera, the first and foremost, the thermal camera, the cost of a thermal camera is going to be the very high. Now, if we look into the principle of the thermal camera, it basically works similar to the pyrometer. Yes, of course. It converts the radiation from the heating source into the certain voltage, and that is being projected into the certain area of a pixel. Now, in case of a thermal camera, the spectrum through which it is recording or taking the signal relatively is going to be the very high, because here it is taking the signal from a broader area. In this image, we could see here, this is the data what I got from the one of the player company. Here we could see the spectrum through which it is taking the signal or taking the spectrum or radiation is going to be the very high. 3 micron to 5 micron, in another case 1.5 micron to 5 micron. Broader the spectrum, more our in the result is going to be. For example, here at this point of time, possibly the temperature is showing 800 degrees centigrade. Here the blue color is showing in the range of nearly 350 to 400 degrees centigrade of a time. Now, ultimately it is giving the relative temperature distribution around the position. So for making reading this temperature, which one we should go for? The peak temperature is nothing but a average temperature, or we can set also the peak temperature what we are getting into the from the camera. But if we are setting that peak temperature, possibly in case of a van, this peak temperature is not something the melt pool temperature. This peak temperature is possibly the temperature of earth just below the electrode, and in case of a TIG and the plasma, possibly this peak temperature is representing the temperature of a electrode itself. So plus since it is the giving the taking the spectrum, which is working on a broader spectrum, it is always going to give us the relative thermal distribution around the melt pool. Plus making the thermal camera taking a reading of a temperature and further communicating for the feedback control system is going to be the very much challenging. So it is a good solution. However, when we talk for the area monitoring, when we want to see the relative temperature distribution. However, when we talk about the monitoring and control, possibly the thermal camera is not the good solution. So now again we left with the one option only, the pyrometer. What is the pyrometer? Pyrometer is nothing nothing but a temperature measurement device. However, it works on the same principle like a thermal camera. However, instead of a broader range of a spectrum, it works on a smaller range of a spectrum, typically for the within the distance, within the range of a 200 nanometer, within this range only, 200 nanometer of a bandwidth. It works on that range only, means a very tight range of a spectrum it works on. So it basically works on a principle. Any body above absolute 0 degree centigrade is going to emit certain amount of a radiation. That radiation is going to get converted or been collected using some sort of optics. Then after it has been sent to the sensors, and some electronics has been generated in order to convert this temperature into the certain voltage signal. It is basically the opposite of a photovoltaic cells, what we could see, or it is a similar of that, we could say. In case of solar systems, once the light is been falls, it generates the voltage. So it does work the same way. However, it has been explicitly been designed for the certain wavelength only. So we can tune it, for there are certain filters which allows only the certain wavelengths to pass through, which is going to fall into the sensor. And it works on a principle of a black body radiation. This is the principle, this is the formula by which we could able to calculate the temperature of a surface. Now, since here we are using certain optics, we can focus this optics to a very small area of the order of nearly 0.1 mm, 0.2 mm, 0.3 mm. Nowadays we can go for with such a small diameter, we could able to focus it, no problem. So it is going to give us the flexibility or the freedom to tightly focus our pyrometer into the zone where the temperature, or the interest where we want to measure the temperature, for making a feedback-based control system, and it is not going to get disturbed by the other energy source which has been there, like an electrode and other. Now here one more thing, in case of a pyrometer, another problem comes into the picture, is basically it is dependent on the emissivity of the surface. Now the emissivity of the material changes with respect to the temperature. So yes, it has got a lot of advantage. Temperature measurement of a moving or overhead object can be made, no problem at all. Very fast response time, exposure time it can measure without interaction, no influence of a measuring object, non-destructive measurement, long-lasting measurement, no mechanical wear at all. However, because of this emissivity, since the emissivity of the material changes with the temperature, and here, here we are talking about the very dynamic process on which we are melting the wire and deposit it. Here the temperature is certainly going to be the very much fluctuating. So, and since the temperature is fluctuating, the emissivity of the body, since it is a function of a temperature, it is going to fluctuate significantly, which is going to possibly going to give us a lot of errors in temperature measurement. So this pyrometer provides a non-contact solution, which is also helpful when the target is not stationary, it is moving. Now, this is possibly the images of the pyrometer we might have been seeing. In the field of a pyrometer, now there's a recently new technology comes into the picture called ratio pyrometer. Are the two independent technologies, a single color and the ratio pyrometer. In case of a single color, it takes the spectrum only from the one zone, and in a ratio parameter, it takes the spectrum of a defined zone, ratio parameter, and two independent monitor and independent temperature. So we are getting the object temperature 1 and T of the same object temperature 2, and we are dividing the T1 divided by T2, since the emissivity of this small spectrum distance is supposed to be almost constant. This emissivity term is going to get cancelled, and we are going to get the almost absolute temperature. So in case of if you are dealing with the process like in RAM, where the temperature distribution is not going to be very much uniform, if the process is very much dynamic, the situation, even using the normal pyrometer, may give us a lot of errors. So moving to the technology like a ratio parameter possibly is going to be the best option to go for. So in order to see the how much error we are getting, if you work with the because in case of a ratio parameter, since it is a recently developed technology, the cost is very high. The normal parameter we can get hardly in a 1 lakh rupees or so. The ratio parameter, the minimum cost is start from the 7 lakh rupees, 8 lakh rupees. So of course the cost is very high. So luckily we got this system. So we try to see how much error we are getting. So we could see in case of with respect to the different parameters, in case of a single channel operation, it gives the nearly 25, nearly 20 to nearly 30% of our error in a temperature measurement. Now this temperature error nearly 20 to 30% is significantly very high when we talk about the feedback based control system. So yes, it is costly. However, it gives the lesser error. So it is best suited for the additive manufacturing and the monitoring and control system. Now at this point of time, possibly we know how to design our WAM setup. We know what are the power source we can use. We know how to move XYZ coordinate system, how to communicate with the machine. We know which sensor we should use for the which parameters we use for the monitoring and control, which is nothing but a temperature. Now we also know which specific sensor we should go for monitoring and control. So now it's a time to go for the depositing the material and trying to control the system. So so this is some initial experiment what we have been conducted. Here we could see when we it is basically a warm tick process, warm tick process. The first layer of precaution is been 150 m, the second layer of precaution 130 m, the third layer onwards we stick to 110 m. But still, if you could see over here, the first layer of precaution, this is the temperature. The temperature was close to nearly 1000 degrees centigrade. However, in case of a fifth layer of precaution, in case of fifth layer of precaution, though the input energy is reduced, the peak temperature is increased close to nearly 1300 degrees centigrade. And we further deposition of layer on the same input parameter, we could see the peak temperature is increasing of the order of a nearly close to 1550 to 1600 degrees centigrade. Now, why it is happening? Why, if we are giving the same amount of energy, why the B temperature is keep on increasing? It is because, again, we'll go to our basic figure. This figure, now we come back to our basic figure. When we are depositing the first layer, we are depositing on a substrate. Usually in case of a WAN, we use thicker substrate having of the order of nearly 5 to 10 mm width and the length of the order of nearly 150 mm, 200 mm, 200 mm, something like that. Means basically we take the thicker plate which is in a room temperature. So in order to make the metallurgical bonding between the first layer of deposition and the substrate, we work with a relatively high current. Since the body is in a room temperature, the heat transfers very fast onto the substrate, and the dominant mechanism of a heat to transfer here becomes the conduction, because the body or the base substrate is already in a room temperature, so it acts like a heat sink. And another loss of energy or the heat dissipation source is basically convection and radiation is basically a lesser in case of a first or initial layer of a deposition. As soon as the number of layers we started depositing, yes, we are adding the mass to the system. However, the volume so which the heat has to dissipate to reach to this heat sink is increasing. The distance is increasing. That means the dominant mechanism of a heat transfer is now shifting from the conduction to the convection and the radiation, which is relatively slower. That's why in case of when we saw this, thermal when we deposit the first layer of deposition, when we go for the 10th layer of deposition, without changing the parameter, here we could see for the first layer of deposition, the build pool size is limited or very small, of the order of hardly 5 to 6 mm, but in this case it is of the order of nearly 15 mm. This is the 10th layer of deposition. It is because over the number of layers of the deposition, over the number of layers of the deposition, we are adding mass to the system. Yes, that is true. However, the volume through which it has to pass through is becoming very much lesser, as well as this body is already on an elevated temperature. So despite giving the some sort of a time interval between the successive layer of deposition, it takes longer time to cool down, and which will further reflected in a bigger build pool size. That means with a lesser amount of energy, the bigger build pool or the same amount of deposition can take place, which was possibly happening over here. Once we are going from when the number of layers is been increasing from the 5th layer to the 15th number of layers, despite keeping the input energy constant, the peak temperature is increasing. However, it has been observed when we deposited further layers beyond 15th number of layers, it becomes almost constant. It is not increasing beyond that because our input energy has got a certain limitation as well. So that means we can consider, certainly we can consider temperature as a source or the parameter which can be controlled to regulate the input energy to a certain value at a desired set point temperature, depends on the material we are dealing with. So, this is basically the idea. We can have a substrate. This is a tick-based torch, tick power source. We need certainly a wire feeder is required in case of a tick-based worm. We can go for the pyrometer. At this point of time, we know why we are choosing the pyrometer. At this point of time, we also know why we are keeping it behind the deposited bit. Then after we have got a certain processing unit and then a computer, and the tick power source is communicated to our control unit. This control unit is also has got the communicating to this XYZ motion control system. This is the system what we have developed in our laboratory. So here we have got the tick torch. We are feeding the wire separately with the help of a wire feeder, and here we have got our ratio pyrometer. The idea is basically whenever we are supplying the certain amount of energy, we are feeding the wire at a constant flow rate. The generated temperature has to be monitored. Based on the generated temperature, it's been calculated or recorded into the certain program. That program is going to send certain signal to the control unit, and that control unit is ultimately sending the signal to the tick power source for regulating the input energy, regulating this input energy so that any desired set point temperature can be achieved. If we are ensuring that means we are ensuring we are depositing at a constant temperature irrespective of the number of layers we are depositing, irrespective of a path of a deposition. So the idea is something like this. Here only power unit and the CNC control unit is connected to our deposition torch. We have got the control unit. We monitor the temperature, resultant voltage, current, and wire feed rate shall be determined. Based on this temperature, it will send the signal to the control unit, and it is going to regulate the power and the CNC unit. Now, most of these pyrometers, if you look into the go to the market and try to buy this pyrometer, most of these pyrometers, they comes with their own user interface platforms. They usually doesn't use the freedom to operate in any other platform. They give their own software. They are saying you have to work in this software. It will give you the temperature reading. However, since we are dealing with the monitoring and control, and we are trying to make all the system by ourselves, taking the temperature reading out of one software is going to be the huge challenge, as specifically for the people like us who's got a mechanical engineering background. So it is going to be a very much difficult. So taking the temperature data out from their software is going to be the huge challenge. So again, we have to go back to the basics, or we have to choose a pyrometer which is giving us some more freedom. So while buying the pyrometer, also we have to consider the many things. For example, most of this pyrometer, all the pyrometer, if we see the basic concept of this pyrometer, what it does basically, it takes the radiation, it takes with the help of a certain optic, it allows the radiation to fall on a sensor, and ultimately it generates the voltage, and voltage is been calibrated with respect to the black body radiation in order to display this certain amount of a temperature using this formula. So if in the pyrometer, if we have got the provision to take out this raw data, voltage, whatever is been generated after the sensor, then possibly we can use this temperature or write our own code to execute, solve this equation ourselves and get the temperature reading in any platform. So if we are able to get the raw data in the form of a voltage, then calculating the temperature part, we can use it using this particular equation. So there are certain manufacturers which give the raw data in the form of a voltage and current. We can take this reading directly and put it into the some platform. Now, since we are dealing with so many machines for its monitoring and control, like in CNC workstation, we have got our power source, we have got the wire feeder, we have got the temperature sensor, we have got, so all those things. The best parameter or the best option I can think of is basically going to be the lab view. So here we have got the temperature reading here, and some communication protocols we have to make through in order to communicate with this. Some uh, further control system we have to make in order to trigger our gas on off, because in case of arc deposition we require the gas, uh, we require certain sort of a switch in order to stop the process completely. So we need to get a pyrometer which gives us the raw data of a voltage or current, so that we can make the platform or the write our own code in some platform like MATLAB, Python, some other can be used. We are using in a LabVIEW platform because it is an advantage here. Now, if you are going for the LabVIEW platform for its monitoring and control process, entire control process, the another thing we have to take into the consideration is basically this pyrometer should respond in a ASCII command. American Standard Code for Information Exchange is a character encoding standard for electronic communication. ASCII code represents text in computers, telecommunication equipment, and other devices. So we have to make sure whenever we are buying this temperature sensor, first it should give us the raw data in the form of a voltage or current, as well as it should respond in a ASCII command, because ASCII commands are human readable. Most of these electronic devices we can communicate with the two methods or the two way of a command, ASCII and the binary. Now the binary commands are very much difficult to write and it is not human readable. So while buying this pyrometer, we have to ensure it can be communicated through external system using its raw data, using some ASCII commands. Here we could see these commands are human readable, depends on the operation mode, laser on off, all those things, emissivity ratio, all those things we could able to control using this certain codes. So while buying this kind of a temperature sensors, we have to take care of many aspects of it in order to ensure it is going to work for our application, which is monitoring and control. Now, of course, then in order to make this control system to feedback based control system, the best idea is to go for the inbuilt PID based controller, the proportional integration or derivative based controllers. It comes with the, if you look into the equation of it, it comes with the three constants that we have to optimize: proportional constant, integral constant, as well as the derivative constant. Now, in order to find the value of it, in order for in ensuring the particular set point temperature, like in this particular case, we are setting the set point temperature to the 1100 degrees centigrade. Then output range also we can set it. Then the real temperature here we are getting 1103.5. Depends on this. This is proportional integral differential constant that we have to set. Now, if we look into the mathematics behind it, how we can able to find the value of this constant, then the entire science possibly is required to ensure that part. Or being an engineer, we can go for the heat and trial method to keep on optimizing it. We can go for the some heat and trial method. We can go some sort of a rigorous experimental work in order to ensure it. Or we can think of some situation on which we can try to minimize the dynamicness of a system as minimized possible. So for that, what we did, we come up with the simple solution. Here is the stainless steel plate. Behind this stainless steel plate, the arc has been generated, and here we could see the plate is glowing. The stainless steel plate has got a thickness of hardly 0.5 mm. Because of the heating from the arc from the behind, it is a horizontal plate. It has started glowing, and we are fitting our pyrometer on the other side, and we are reading the temperature. Now, since we are measuring the temperature behind the plate, then the effect of a arc is not coming. At the same time, effect of external radiation, other radiation like an arc radiation, like whatever the light is coming out from the arc, all those things is not participating over here. Anyway, it should be minimum in case of a ratio. However, still it is not participating. So then after we started trying to find out the value of this constant by heat and trial method, this is the simplest way we could go for. And with the certain heat and trial method, we could see the incremental and decremental control temperature with respect to that time. Here we could see we could able to control the temperature. Whatever the temperature we required, we could able to control the temperature. We are controlling the temperature. That means we are controlling the input energy of this peak power source. Here, basically in this case, what we are doing, we are measuring the temperature. Over here, we are controlling the input energy such a way that desired temperature, set point temperature can be achieved. We are controlling it by regulating the input energy through the peak power source. We can control both by hitting it to the certain temperature, then reducing it, and from the certain temperature to the increasing it. When it is focused inline, then once we could able to achieve it, in order to ensure these constants are going to work always, or in order to modify it further so that it can work in a dynamic environment, we can off-axis deposition or off-axis measurement can take place. So here what we did in another case, this is the heating source, and we are measuring nearly 8 to 10 mm away from the peak heating temperature. Now here the temperature what we are getting is basically the conducted energy. So but here still also by certainly optimizing these parameters with little bit of a modification from the previous case, from this first case, we could able to control the temperature. Now, once we are able to reach to this state and we are getting the some value of this constants, this PID constants, now it is the time for going for the moving heat source without any deposition. Just move the heat source and try to again optimize if there is a certain something is required to optimize this constant. And of course, with a certain heat and trial method, little bit of up and down, we could able to achieve it. Once we reach to this system, this stage, possibly now the time to deposit a single bead, multi-bead. Now, uh, all this information was required to train the system such a way we can get the best value of this constants which will work in all the environment, whether the heat source is stationary, whether the heat source is off axis, whether the heat source is dynamic. In all cases, it will work. All this information is basically required in order to train our system. It will work in all the environment. Otherwise, in actual environment, when we start depositing, the process is going to be very much dynamic. Plus, we are measuring it behind certain distance. So there again, lot of a effect of a dynamicness of a melt pool comes into the picture. We saw in that thermal video. So the temperature is going to be a very much dynamic. So we have to ensure our system works on all kind of environment. So once we could able to ensure that part, we could deposit single bead, multi-bead, no problem. Here we could see within the, we are depositing the low alloy steel. We could able to hold the temperature. We are measuring it nearly 10 mm behind the earth, and we could able to hold the temperature 1200 degrees centigrade, 1300 degrees centigrade, 1400 degrees centigrade, or even in using the deposition of a bead itself, we could able to control the temperature using the deposition itself. From 1400 to 1200 or 1200 to 1400 centigrade, we can able to regulate it. Now the question comes, what advantage this kind of a control system gives us? It is basically, here we could see, whenever we are with respect to the different temperature, when we, let us suppose when you're working for the 1200 degree centigrade, the bead width is the lesser and the bead height is more. When we're going for the 1400 degree centigrade, the bead width is more and the bead height is lesser. Of course, because we are dealing with a 1400 degree centigrade, that means we are giving the more amount of energy. That means the physical characteristics of the deposited bead changes with respect to the set point temperature. Now, when we try to see the mechanical properties of it, yes, of course, it is also changes with respect to the set point temperature. Here we could see in case of a 1200 degree centigrade, the hardness was high. In case of a 1300 degree centigrade, it was relatively low. In case of a 1400 degree centigrade, it was a further low. That means by controlling the temperature, we can able to control the bead physical properties, bead width, bead height, dimensional accuracy can be controlled. At the same time, we are also controlling its mechanical properties. Now we have got a lot of, we can make it applicable not only for the works, but also the cladding, alloying, different kinds of weld joints. We can make it applicable, no problem at all. At this point of time, possibly we could able to control it for the desired shape as well as the desired mechanical properties. Now looking into the some data, how much time it takes to stabilize it, how much the error what we are getting. So typically what we are getting, the error in this system, the developed system, is of the order of hardly 1 to 0.3 to 1.67%, which leads to 5 to 25 degrees centigrade only. And in case of a dynamic heat source, it goes hardly from the 1 to 1.67%, which in terms of a temperature, hardly in the range of 15 to 25 degrees centigrade. Now let us talk about the, if we talk about the melting point of this steel, then it is of the order of very close to 1450 degrees centigrade. Considering that 1450 degrees centigrade, the error in this temperature range is possibly very much lesser. So with this way, we could able to deposit any material. We need not to optimize it, because for the most of the optimize the parameters, because for the most of the material we know that its melting temperature. Let us suppose if we optimize this proportional integral differential constant for the mild steel, but we can work on a stainless steel, mild steel, we can work on a stainless steel, we can work on a titanium, we can work on a inconel. By changing the material should not affect the process, because this constant with respect to the process dynamics, it has been completely trained. So whenever, even if you are working with the different materials, we can set our desired set point temperature. So we need not to go for the exhaustive experiment or rigorous experiment in order to optimize the parameter, in order to get the desired bead properties as well as the bead mechanical properties, bead shape and bead mechanical properties, or ultimately the desired shapes. So that was the idea, and I think we are succeeding completely. But again, in case of a van, the post-processing remains the matter of concern. Despite controlling, monitoring, and control, and achieving the good success on it, means in case of a van, since the bead melt pool size is going to be the bigger, the deposition accuracy is going to be certainly relatively poor compared to any powder-based, laser-based process. So in order to minimize the post processing, again we can come back to our first slide where I've been showing, we can machine it, depends on an application. The rest of the surface where there is a certain spatters, some oxidation is there, we can go for the conventional are the well traditional finishing method called parallel finishing, in which what we do, we have got the abrasive particles, typically what we use silicon carbide we use, and then after we can put this part inside of it and we can rotate this panel or vibrate it in order to statistically clean all the surface, remove all the oxide and some spatters. So this is a system what we built in our laboratory. Here is the drum in which we can feed our this abrasive particles, and here we have got some joints, and then after we have got the three-phase motor and some variable frequency controller. Here we got, in order to control its rotation, and here we got the rotational joint, and here we got the certain suspension system, so then it can, with the, when it is rotating, it is making the vibration good amount, and so that the cleaning can take place faster. So in order to optimize the how many hours or how many minutes we should clean it, we should try to optimize the parameter again with a certain rotational speed of course. So we can take some standard shape like this, and within the distance of time of 1.5 hours or so, we could able to see it's completely cleaning this surface. So within the distance time duration of 1.5 hours, possibly we could able to clean our one part as well. And here we could see there is a S deposited sample. This is the clean sample. There is a S deposited sample. There is a clean sample. Is a S deposited clean sample. Similarly, over here, all the oxides is been removed. Some amount of spatters have been also been removed. Yes, this parallel finishing cannot completely replace the machining requirement. However, machining we can selectively do for the desired locations only. However, the rest of the area, we can go for the some innovative ideas like this barrel finishing. This is a conventional method of cleaning for its rest of the body, for removing the oxides, some amount of a spatter. So now, if we are looking back, all these processes, whether it is a powder bed fusion, blown powder method, warm, high energy, deposition method, all these process has got a certain advantages and limitation. At the last, I would like to say, all this process has got the certain advantages, limitation. In some case dimensional accuracy is good, some case the cost is effective, some case deposition rate is good, some case the intricate shape can be made, some case the support structures are not required, some case support structure making is very much difficult. However, as such, all these processes are not in a competition with each other. Depends on an application, we have to select appropriate process. For example, in this particular lecture, we are talking about the worm. Then we started from the basics of a worm. We made our own CNC workstation. We know which power sources we can use, what are the constraints we have to follow. So then after we come across the limitation of a support in a worm, so we overcome that problem as well. Then after we looking for the control, how we can go for the control, which parameter we should try to go for the control. If we are selecting that part as a temperature, so it will be the best parameter to control. Then which device we should go for the measuring the temperature, like a thermocouple pyrometer, temperature, this thermal camera. Once we know that part, in case of a pyrometer, also what are the constraints it might have that we have to take care while buying the system, because these systems are very, very costly. The sensors are very, very costly. We have to make sure we are not making any mistake. Once we are achieving that part as well, in that, after that also, what are the other constraints we have to write our own code. It should be communicated with the ASCII commands. Then after certain rigorous experiment in order to train our system. Once we are able to achieve this, just control is possible, and we can monitor the process in process, no problem at all. So I think we are just end up with that time. So that's it from my side. Thank you so much. If there is any question, I'll be more than happy to address.
Yeah, thank you, Dr. Yuvraj. That was a well-made presentation and briefly you have taken up the each and every case of your like attempted work. I think it's like a year of it's a years of work. I mean, that you have made a like wonderful work and you have presented in a well organized manner.
Thank you.
I hope you have enlightened everyone who are working in this field of additive manufacturing. They must be like happy to hear your lecture. Yeah, any questions from the audience? Yeah, many of you might be working in the field of manufacturing and smart manufacturing and all. So clear your doubts.
At this point of time, they might not be having any question. However, if they have any question, they can always come back to me and go to me.
That's always true, but some people raise it because they might be interested in something else. They are also might be working in similar kind of works.
Right.
So maybe it's a good chance, no, like to interact with you directly, and then they can ease off their doubts. However, they are having.
So most of these results, what I have presented in this one, this presentation is already available online. They can go to my publication.
So whatever the work you presented, already published, no? Published work.
All of them are already published. They can find it in my published works. So they can find in a more detailed manner if they want to go through. No worries at all.
Okay, that's great.
Okay. Thank you, Dr. Yuvrajji. You have presented your work beautifully, sir. Thank you very much.
Thank you. So shall I leave, Dr. Rama?
Yeah, Doctor, sir, you may leave, sir. I mean, we are having some important information.
Okay.
So we will continue. So you may please leave.
Sure.
Good night, sir. Yeah.
Good night. Bye.
Bye.
Yeah. My dear participants, very good evening once again. I would like to share some of the few important points that is to be noted as far as this FDP is concerned. The first one, tomorrow we are conducting first examination. We need to conduct 2 examinations. Now just I am opening the assessment procedure. Just I hope my screen is visible. Ramakrishna, is my screen is visible to you?
Yes, sir.
Okay. Now, please, all of you, please look at this. Most of the participants might not have gone through this document, so I am putting here. So, to get a certificate, each participant must get 70% of marks. There are 6 components in the evaluation. First one is attendance carries 10%. If you got 80% attendance, you will get 10%. Then 2 assessment tests, one after each week. So tomorrow we are conducting the first assessment. At the end of the session, we will post the questionnaire through Google Forms that will be there in the chat box. So please fill the answers and submit back to us, which carries 20%. The second assessment will be conducted during the offline session. Third parameter is the 2-page article summary. What is this 2-page article summary? Yesterday we have given 2 papers. So each one has to submit for each paper 1-page article. There is certain format is also there that I am going to show here. And teaching practice, every day we are giving 1 hour for teaching practice. Each faculty, each participant must give at least 10 to 15 minutes of teaching. Then report or outcome of industrial visit. On Tuesday we are conducting industrial visit. That report has to be submitted. It is a team wise. And reflection journal, this carries 15 marks. So all these 6 components for the assessments is to be carried out. Now coming to this formats. So this is our offline schedule. We already prepared the offline schedule. I request all the participants every day please available at 9 a.m. Now MCQs. Now here you can see on Thursday, last session we are conducting second assessment test, multiple choice questions. And also you can see last hour, every day last hour we are allotting for teaching practice. Okay. Now this is our assessment procedure. Now this is reflection journal format. Reflection journal format. You need to submit in the written format. Now you can see identify 3 key learnings from FDP bullet. This is to be done at the end of the session. Now you can see this is the schedule. Now last day, Friday, okay, Friday after lunch we are keeping the time for visit report, reflection journal, and then valedictory. So during this time you can prepare all these things. Okay, so these are the 3 key points. Then list of 3 key lessons that you will implement, and then share an implementation plan for your 3 key lessons. So all these things you need to fill. Only 3 points for each one, 3 points. And coming to the reflection journal format. So key principles or practicals from the article. As I mentioned, we have given 2 papers. For each paper you need to submit like this. Okay, 1 page report. Key principles or practicals, and then application of principles or practices in your function. So here key principles or practices, this is to be discussed among the team. And all the team must have the same points. Whereas this one, application of principles and practice in your function, this is individual has to submit. And once again, key takeaways from the article, this is once again 3 to 4 bullets from the team. So what we will do is, during the offline session, first day after the inaugural session, now look at this, after the inaugural session, during this article 1 discussion, we have given 1 hour time for article 1 discussion. During this time, we will divide the total participants into some 7 or 8 teams. So each team has to discuss the article 1, and a report is to be submitted in the format what we have shown. Article 2 discussion is on Tuesday. So by Tuesday, both the articles will be discussed. So that's what I mentioned in the yesterday. I request all the participants, please just to go through all the 2 articles so that this time can be utilized effectively. And then tomorrow, once again I am informing you, tomorrow after end of the session we are conducting first assessment test. And if anybody is having any doubts regarding this, now we can ask. And if anybody is having the accommodation, we are providing a limited accommodation for limited participants. If anybody is required the accommodation, please let us know by tomorrow. And this is a chargeable basis, of course. So these are some of the important points that I would like to share, and if anybody is having any doubts, please ask now so that everybody can get benefited. Dr. Ramakrishna, you can post the feedback. Please.
What time the assessment will be there, sir? Test will be there
tomorrow after the session, Sachimohanji. Probably maybe 8:30. Most of the sessions are closing by 8:30. So we will conduct the exam at 8:30.
Yeah, tomorrow we requested the resource person to wind up his lecture by 8:30 or 8:40 maximum. So that after that it followed by the exam. We will give you a sufficient amount of time. Don't worry about it, and it will be in fundamental questions only out of this lecture series.
Now this is the once again I am just showing you assessment. This one 70. If you got 70% out of all these 6 components, if you get 70%, then you will get a certificate. If it is a 90% and above, you will get distinction. 10% will be given to attendance for 2 assessments, that is 20%, and then article summary 30%, teaching practice 15%. Outcome of industry report, that is a report on industry visit 10%. It is a team activity. and the reflection journal 15%. Now you can see clearly he mentioned, clearly Atal instructions are given that the 5th and 6th must be conducted at the last session. So same thing we also doing as per the, strictly as per the directions from Atal. Okay. If there are no doubts, then thank you one and all. Good night. Good night to everybody. Once,
Sir, feedback link has been shared. Maybe
feedback link is
all
feedback link is there in the chat box. Please fill your feedback. And tomorrow we will meet at 6:45. And tomorrow is the last day for online sessions. Online sessions. Okay. And it will be closed by writing your first assignment test. Thank you. So many are there.